And not only can they be, they must be. Energy cannot be created or destroyed. We'll talk about the law of conservation of energy if you haven't already. Energy cannot be created or created or destroyed. It can only be transformed or transferred. So then, where is the source of the vast majority of energy on our planet coming from?
The sun.
Yes, as in the picture right here. The sun, how does it show up to our planet? Rays of light. So the sun sends us energy in the form of light. How do you get access to that energy? There's you, next to the giant bunny. It's a terrifyingly large bunny. Or you're really small, I'm not sure. How do you get the energy? There's a process of transformation. What's the process? Sort of. Yeah, Liam? Eating the sun? So what does the light hits the planet? Where does the energy go? Into the planet. What's the process called? Photosynthesis. And photosynthesis is the process of turning sunlight into what? Sunlight and carbon dioxide and water, and it turns it into what? It turns it into more plant, but it also turns it into... So what is the... When it turns into plant, what form does it take in the plant? Sorry? No. I want a specific... What is it in the plant? No, it also produces oxygen. Oxygen leaves the plant. You need the oxygen and you need the stuff from the plant. What's the... Be more specific than nutrients. No, it is not amino acids. Those are proteins. Plants are not a great source of protein. Yeah. Nope. What is the most foundational? Carbs, yes. You're going to hit it eventually. Why is bread full of carbs? Well, bread is made of flour. Flour comes from wheat or a whole host of other plants. Flour is a plant-based product. You're getting your carbohydrates from those plants. The structure of those plants is what the carbs get used for. They release the oxygen so that you can breathe in the oxygen. That is a change from light energy to what form of energy? What do we call the form of energy that you take in as food? Where did we talk about carbs and oxygen in this course? What was the chapter? We did. In chemistry, this is chemical energy. Yeah, we talked about carbs. They were a product of a combustion reaction. We talked about it. Last section, the second last section of you were awake because you burnt yourself. That's why you missed it. But we talked about them there. What kind of energy is what? Chemical energy? It's the energy present in the bonds of the different kinds of compounds that you consume. Because if you don't get your energy from the food that you eat, where does the energy? You don't have any other access to energy. If you stop eating, you will eventually die. Like that's just if you stop breathing, you will die, right? Like because your body runs out of the materials that it needs to function. Its source of energy gets depleted. When you don't have access to a source of energy, you die. It sounds dark, but that's what it is. There is a process that once you take in the carbs, you take in the oxygen, your body undergoes another process. You take in the chemical energy, what does your body do with it? What's the process called? It is not protein synthesis. It is not a synthesis. You don't have to eat the rabbit, but you could eat the rabbit.
I don't want.
You don't have to.
So,
But you need to get your protein from somewhere. Beans.
cow.
You could eat a cow if you'd like.
Okay.
Fish. Again, beans are a good source of protein. But what does your body do with it? There is a process. You will learn about it in grade 9. 2 words. One of the words starts with a C. The other word starts with an R. Sorry? This process happens in your cells.
Give us the first word.
It starts with cell. Cellular. Cellular. Starts with an R. No. No. It's related to breathing. Respiration. Cellular respiration. Okay, so photosynthesis turns sunlight, water, and carbon dioxide into carbs and oxygen. Your body turns around and takes those carbs and those oxygen and turns it into CO2 and H2O. The things that photosynthesis needs, carbon dioxide and water, your body produces during cellular respiration. You breathe out the CO2. You sweat and pee out the water. But how does the energy get transformed into something your body can use? Does anybody know? There's another product of cellular respiration that your body produces. No. No, it has a name. It's a 3-letter name. Sorry? No, Angel, say that again. What did you just say? I thought she said the thing. Did you not say the thing? Oh, you didn't say the thing? It sounded an awful lot like the thing. There's a molecule called ATP because it gets discussed in grade 9. Well, maybe if you had me for grade 9, it was disgusting. Yes. ATP stands for adenosine triphosphate. It is the molecule produced in cellular respiration that your muscles use to move. Your muscles need this adenosine triphosphate in order to do the things. How do you know, or then, sorry, I'll say this way. What then does your body do with the energy? How do you know a body is using energy? What are the 3 ways that you know a body is using energy? Sorry? So sweating is just a production of heat. So you're producing heat. What else does someone who's using energy produce? Yeah, that's not what I'm looking for. Breathing is not a form of energy. No. This is all about energy transformation. So light turns into chemical energy turns into heat energy, which is a form of light. What other kind of energy does a body transform chemical energy into? Sorry? No. There's no such thing as cold energy. Cold is a lack of energy. If you feel a body that's cold, it means the body's dead. Which means they're probably dead. We're not all Captain America here. How else do you know that someone has energy? Put your phones away, gentlemen. None of you need to be playing games now. Talking. Changes it into sound. And movement. Everything you do can be summed up as this. The expenditure of energy turned into movement, sound, and heat. That's all you do. Your body takes chemical energy and produces these 3 kinds of energy. That's the whole premise of the movie The Matrix. You're just functionally a battery, according to the movie. It's quite interesting. But we use light another way. Light can be taken by one of these. What's this? It's a solar panel. Solar panel also called a photovoltaic cell. Yeah, no, that's actually what they are. Don't tell me nobody calls it because I just did. Photovoltaic cell. A solar panel is made up of a bunch of these. Yes, write down the word photovoltaic cell. Photovoltaic. Photo meaning light. Voltaic has that word volt in there. How are you familiar with voltage? Electricity. So a solar panel takes light energy and turns it into electricity. What is electricity? No, that is not what electricity. What is electricity? You all should, grade 9 physics, guys. What is electricity? No. What about the electrons? The electrons have to be? Electrons have to be what in order for electricity to be happening? Nope. No, pressure is not a word. Electrons are negative, but that's not what they have to do. How do you, sorry? They have to move. The electrons have to move. So what is this? Well, it's taking light and turning it into motion. Electricity is just the movement of electrons. We call it current, but it's just another form of motion energy. And then what happens? Well, if it's an old school light bulb, you run it through the filament. The filament slows it down, produces resistance. When resistance occurs, what two forms of energy does a light bulb produce? Turns it back into light and heat. If you have a really crappy light bulb, what else does it turn into? Sorry? Sometimes lights buzz. No, not combustion. Sound. Sound. That's not combustion. And in fact, I should go back and if you're telling me that an exploding light bulb is a combustion reaction, I'm going to go back and I'm going to change your grade on that chemistry unit test. Because we talked about exactly what combustions are. Except Dennis. Dennis got all those questions wrong. Not all. You got the matching part right. But Dennis was away for 4 weeks. So what's your excuse, Josiah? Which is why I'm threatening to go back and change it. When I'm asking you something from a chapter that we did 6 weeks ago and now you're giving me the wrong things, tells me you don't know what you were doing. Put your phone away, Malik. If I see it again, it's mine. I will give it to Josiah. Okay, so this is, and it's just all our whole existence is. Our whole existence is just transforming energy from one form to another. Sure, we do things with it. We go to school, we have jobs, but all we're doing is just expending energy that we receive from the sun in the form of food until our bodies can no longer do this, and then all of the other bonus activities no longer happen. So, energy and systems. You would get vaporized. The sun would use you in a process that we'll talk about in a couple days. You would get converted back into energy pretty devastatingly. Okay, so energy and systems. When we analyze energy, we have to talk about systems, and we've talked about systems before. We talked about systems when we talked about chemical reactions, and chemical reactions can occur in an isolated system or in an open system. In an open system, what was allowed to happen? Matter Matter can escape an open system. In a closed system, matter is stuck, but energy is always allowed to flow, open or closed. And so we're not going to talk about open and closed systems now. We're going to talk about isolated versus not isolated. Different than closed and open. So a system is by definition anything under observation. You get to define what your system is. Right now, like for example, the system I could be observing right now is you guys. I could isolate my system to the 24 of you who are 22 of you who are here. Or I could expand it a little bit and I could say, well, my system is the room. Not only am I watching you, I'm watching all the other crap that's going on here, like that bug that's flying over by Elijah. I could expand it to the hallway. It's actually, yeah, it's on this side of you, Elijah. It's a fly. I could expand it to the hallway and I could observe the people over there. I can see into Mr. DeVries' room. You, as the observer, get to choose how isolated your system is. Anything that is not part of the system that you choose is what we would call the surrounding. So this is your system. Let's call this zone your system. And this would be the surrounding. And if we take all of the systems and all of the surroundings and we put them together, what have we got? If you take every possible system and all of its possible surroundings, what are you talking about now? And what word can we use to define everything? It starts with a U. The universe. The universe is every system and all of the surroundings. The universe is the ultimate system, where we look at everything in and there's nothing beyond. And within that system, all the energy that is here and will ever be here is within our universe. So when our universe runs out of energy, and it will one day, the universe will cease to exist. So let's zoom back in and let's look at two different kinds of energy, kinetic and potential. The two main kinds of energy that we're going to look at, oh, you guys are difficult to contain right now, aren't you? The two main kinds of energy that we're going to look at in this unit, Luca, are kinetic and potential energy. What's kinetic energy? Vikram, what is kinetic energy? Energy from movement. So kinetic energy is the energy of movement. Okay, so let's talk about movement. One of the energy is, until we actually start breaking it down and calculating it, energy is pretty abstract. How, like, we have no good way to measure energy. It's not like I could look at any of you and say, you have this much energy, you have this much energy, and to actually have a numerical measure for Josiah has this much more energy than Kenshin. But we can make some observational thoughts. As a class, let's talk about Kenshin and Josiah. It doesn't have to be Kenshin. It could be Ikpreet. What do Kenshin and Ikpreet have in common that I'm isolating them from Josiah? I could lump in Dennis and Luca to Josiah too. How are those three gentlemen quantifiably different than those ladies over on that other desk? No, we're not talking about biology, now we're talking about physics. If you had to talk about the amount of energy possessed by those four versus the energy provided by these four, which one would you say has more energy?
Definitely Josiah, not
well, definitely the guys, right? Like, you can say, okay, these guys over here, there's more activity. They're chatting a whole lot more. I could lump in these two gentlemen too.
No.
Or even worse, like it could just the three of you. Like it's Thomas, Luca, and Dennis. They're bringing the energy down. You three have more energy, even though we're kind of similar to all these four don't have as much, and just by looking and observing, we can say, you know what, the volume from that table is lower, the movement at that table is lower, the movement over here is much bigger. If any of you have been watching the league,
It's been hard for you to stay still his whole life. Which is not a bad thing, but we can make an observation. Malik has more energy than Kenshin. Just because the motion is there. If you had to describe, so kinetic energy, when I'm talking about energy, one way, and I think a good way to say, for you to have a picture in your head about how much energy is present in an object, Josiah, stop talking, please, is to ask yourself the question, how much will it hurt? How much will it hurt? That's a great way to ask yourself to evaluate how much energy is available in a system. At this stage, right now, some of you have, if I was to ask you, I don't know, to pick on someone, I want a direct answer from Michael. I would like an answer from you. Which of these two people, Malik or Kenshin, would you be more concerned about right now if you started to bug both of them? Let's say you're friends with Kenshin and Malik, and you know what drives them both crazy, and you just start poking at them. Which one of them do you think would respond to you faster? Malik or Kenshin? Sorry? Probably Malik. Malik's already elevated. It might take Kenshin a little bit more. So, a way to measure this, Malik will hurt you faster than Kenshin will. Kenshin might hurt more, but yeah, I don't know.
What if Malik's like really nice guy?
Okay, so let's talk about kinetic energy. Kinetic energy is the energy in motion. Are either of you remotely concerned about me right now? Just, you don't know what I'm doing. I'm standing here kind of awkwardly. No, you're not concerned about me. But what if I started like running at you down the hall? Is that more concerning? You're way over there, and I just decide, Memphis, I'm just going to start running at you. That would be concerning to you, yes? At this stage, physically, you have nothing to fear. But if I start running at you, that's concerning. I have more energy, I have more capacity to hurt you. If I'm just barreling down the hallway at you, there's something there. So there's different kinds of kinetic energy. Would you be more or less scared if I were smaller? If I were my son, for example, at 2.5, just barreling down the hallway at you,
Yes.
would you be more or less afraid? You wouldn't be afraid at all.
Well, if you were a kid, no. But if you were a grown adult, that short chasing me down the hallway.
Well, that's a whole other offensive conversation that we're not going to be part of. Let's avoid that one for a second. But like, if my 2-year-old was running at you, let's say my 2-year-old and I are running side by side down the hallway, which of us would hurt you more if we ran into you? Me. So somehow I possess more, even though we're moving at the same speed, somehow you know intuitively that I possess more kinetic energy than my son does. So kinetic energy is not just a property of the movement. Kinetic energy is also a property of size. In science, what concept do we use to talk about size? Mass. So kinetic energy is a function. Ouch. Oh. Kinetic energy is the function of, or it's related to, the speed at which the object is moving and the mass of the object. And I think I've talked with you guys about this before when we were talking about the wavelengths of light and as far as mutations. Like if we talked about, speed and mass, my son and me kind of just trucking down the hallway, you know that if he hits you, it wouldn't hurt you as much as if I hit you. But the speed of the object also has something to do with it too. And I think we talked about it. If I brought a bunch of 22 bullets and I just started plinking them, I tossed them at you, not concerning. 22 bullets are small. You might ask yourself, well, why we don't have a box of bullets in school? But that's a totally different question. But do I have a 20? Yes, I have a 22 at home. Yes, I do. I could bring a box of 22 ammunition to school. I'm not going to, but I could. So, but if we were to go to a field trip, there are PE classes, outdoor education classes, that will go to the gun range.
I want to be in that class.
No. If you were to go to the gun range, all of a sudden a bunch of 22 rifles pointed down range is a lot more concerning. You don't want to get in front of those. Even though it's the same size little dinky thing, what is concerning now about those teeny tiny little bullets? The speed at which they move. So they would hurt a whole lot more than if I was just plinking them at you, even though the size is the same. Actually, the size is smaller because you lose the whole casing. The thing I would be throwing at you is actually larger than the bullets are. Yes, hello, Lachlan and Liam. Love you too. Sorry? That's a whole nother conversation. We're not talking about bombs. Unrelated to kinetic. Okay, so kinetic energy is the energy of movement related to mass and speed. Potential energy then is this other one. Potential energy is one of those, or potential is one of those buzzwords. What does potential mean? The possibility. So potential energy is the possibility that something could hurt you later. And the more it could hurt you later, the more potential energy exists. So let's talk about a particular kind of potential energy that I will define later. Let's go over here. I've been picking on the same group of people. Let's go over here to this table. We'll talk with Vikram. Okay, so I've got my coffee cup over here. I've got a highlighter over here. Do either of these, as they sit, have the potential to do any work?
I mean,
Or sorry, do they? Let's go back to the scale I was talking about before. What are you doing? You don't need to deliver it. You're sitting across the table. Just hand it to her. Malik has a lot of energy. So, do either of these have the potential to hurt Vikram as they sit?
Yeah. No, not
really. On their own, just sitting there?
I mean, unless he like hits his head. I don't know.
Like he would have to go out of his way to do something dumb to get hurt by either of these objects right now. Yeah. But what if I did this? Do either of these objects now have the potential to hurt Vikram? Yes, they both do. Why? Because I'm holding them above his head. Which one would hurt more? The marker would hurt more? Should we test on Malik?
Yes.
Honest answer. Which one would hurt Vikram more if I dropped them both? This. And you don't know how much coffee's in you. If I haven't drinking this yet, I mean I have, it's empty. But if this was also full of a liter, how much is it? Probably 750 mils. 750 mils is 750 grams. It's almost a kilogram. Yeah? 1 liter of water weighs a kilogram. It's beautiful how they all relate. So 750 mils of coffee would weigh just over 750 grams. Because it's not just water that's in here, it's all of the other dissolved stuff, so it'd be a little heavier than that. And the highlighter, like, not overly painful at all, right? So when you're talking about potential energy, and specifically if I'm talking about hurting Vikram this way, just by letting them go, what's doing gravity? So we call this gravitational potential energy. And whichever one would hurt you more is the one that has the greater potential energy. So if each of these has one of them has a greater potential energy than the other, then, yes, who said that? Then the gravity, when we talk about gravitational potential energy, the gravitational potential energy, hey guys, Vikram and Paris, keep your hands to yourself. The heavier one, the more massive one will hurt you more. So gravitational potential energy is related to the mass. What else is gravitational potential energy going to be related to? Let's go back to Vikram. It's not speed because they're not moving yet. They're just sitting there. What if I did this? Is that scary? If I did this? Yes, that's scary. If I stood on a chair and went way up there, that would be even scarier. Vikram's going to get hurt more the higher these things go up. And so gravitational potential energy is a function of the mass, and it's a function about how high they are above whatever they're going to impact. What if I was somehow able to teleport Vikram and I to the moon? We'll hold our breath, it'll be a little chilly, but if I held these above Vikram's head on the moon versus here, which one's more concerning? Here. Why? There's
There's more gravity here. So gravitational potential energy is a function of how much gravity there is. It's a function of the mass of the objects and how high you are above wherever they're going to impact. Those are the things that, whether you realize it or not, those are all of the things that your intuition is evaluating when you look at this and say, yes, that's going to hurt more. So that's this. This is a waterfall. Waterfall, when the water's up here, if this is where the water is, there is gravitational potential energy. Potential energy. Because the water is going to fall all the way down. It's a function of this height. It's a function of the mass of the water. And it's a function of the gravity at the location. So that's one. What's this? Vikram. This is potential. It's a slingshot. So what kind of potential energy is here? I'll make it really obvious. What's this? Rubber bands are also called elastics. So this is elastic potential energy. And elastic potential energy is a function of what? Gravitational is a function of the mass, the gravity, and how high the thing was above where you are. Let's take a look at some of these. I've got some rubber bands. And I've got this bad boy. Spring. This would be the most terrifying whip. Spring whips. Would suck to be hit by. All of these are springy. They all have elastic potential energy. Let's talk about them. How are these different from each other? These three objects. Size. So, what is scary? We're talking about size. What is scary about elastics? Are they scary? Really? Here, hold this. Oh, so there's a difference. So right now, this isn't hurting you, is it? No, okay. Okay, hold your end. Do not let go. I don't want to get hurt either. I'm not going to let go. You don't let go, I won't let go. Okay? So now there's a reason why we're both concerned, right? Why are we both concerned? Because there is a potential here that one of us will betray the other. If you throw something at Lexi again, you will leave. But I saw you throw it back. This is concerning, both of us. We are deeply trusting the other person not to screw this up. Actually, I did not expect you to just release it. I expected you to just snap it. Because I gave you permission to. So no, now I'm not going to. So this one, but look at these. Okay, so which one of these is more concerning? The little one or the big one? Why? Because this one's going to be harder to pull back. This one will be easier to pull back, and so there's a function there. It's the property of the spring, called the spring constant. We'll talk about that in a little bit. This guy here, hold your end. At the very end. And I'm going to hold this. And so here's a big spring. If I step back and say, okay, so this is, if we let this go, it's just going to fall. Like, we're not really pulling on this at all. If I pull this one, the same distance we pulled that one, is this concerning at all? Like the extra couple centimeters I gave. Okay, Victor might like to go for a walk. Oh, the other side. Maybe this side. This time when I say let go, actually let go. Okay, go for it.
going to the other classroom.
I'll tell you when to stop. Okay, you're good. Okay, now at this stage, compare this to those little rubber bands. When I stretched it the same amount as those ones, it wasn't a big deal. This spring is easier to pull than the rubber bands are. But now, look how far away he is. Exactly. This is my point. He is halfway down, almost, you know what, go all the way to the end of the bulletin board there. Okay, stop right there. He's at the fire escape. That's a pretty good distance. You can still hear me, they cannot see you. Oh, careful. Killing grade 9s now.
Yeah.
Okay, so now this should be concerning. If you were on the receiving end of this thing, there's a reason I'm standing on it, not holding it with my hands. Okay, let go, Vikram. And the thing came back in on itself very quickly. So when you're talking about elastic potential, thank you, Vikram. When we're talking about elastic potential, it's not mass and height and gravity anymore. Now it's the extension, which is how far it's pulled from, we'll call it the rest length. Oops, sorry. The extension, how far it's pulled from the rest length, and how hard it is to pull. The how hard it is to pull has a name. Every spring has a measurement of how hard it is to pull. Some are really easy. This big spring that I had here, this floppy thing, really easy to pull. If you're building a trampoline, though, hands up if you ever put a trampoline together. Those springs are really, really hard to pull. They have a larger value for this concept. This concept is called the spring constant. And every spring that is ever made has a different value for this, how hard it is to pull. The larger the number, the harder it is to pull. And we can measure this. So this is potential energy, different kinds of potential energy. And this blank right here is the possible. The possible energy of an object as a result of its condition or its position. Questions, comments, concerns so far? When you're ready, flip the page. So we've got types of kinetic energy, and we've got types of potential energy. This first one is the energy of an object in motion. We call that mechanical kinetic energy. Mechanical kinetic energy is just the movement of a normal-sized object. If instead we're looking at other moving, like light is just moving really teeny tiny particles called photons. That's called radiant kinetic energy. And over here, like, so if this is light, maybe visible light is over here in the middle. Microwave is going to be over here. And X-rays are going to be over here. I mean, if you look at what's going on here, like the closeness of the waves, the more tightly packed the waves are, the more you should be concerned about the kind of light that you're experiencing. X-rays are concerning, microwaves are less concerning. Microwaves will burn you. That would suck. X-rays will give you cancer and possibly vaporize you. That's a lot. Vaporization and cancer is more concerning than you have a skin burn. Yes? We agree? Okay. We've got this, the energy of the random motion of particles in a substance. That's a weird definition. This is thermal energy. Thermal energy, that's the next one.
Thermal energy is related to this concept called heat. It's not the same thing, but they are related. Heat and thermal energy are related. Thermal energy is the movement of all of the particles in an object. Heat is the average movement of all of the particles. Those values are different. Let me see, you look perplexed by what I just said. Let me give you an example. So if thermal is the energy of all of the particles, you guys are aware, have we looked at the kinetic molecular theory at this point in your education? It's the idea that everything you see is made up of particles, and those particles are moving. In a solid, they're just stationary, but they're jiggling back and forth. In a liquid, they're freer to move, and in a gas, they just go everywhere. We've seen this before? You're supposed to learn this in middle school? Okay. Those different kinds of movement are what we're talking about when we talk about the random motion of particles in a substance. So gases will have a higher thermal energy than the table because the gas particles are moving quicker and more violently than your table particles. But because thermal energy is the total, all you need is a really big stationary object to have a lot of thermal energy. Like an iceberg, for example. Typically, we would think of an iceberg as being very, very cold. But because there are so many particles in an iceberg actually has a ton of thermal energy. Way more thermal energy than a lit match, for example. Even though it's much colder. So on. Are you hearing the things I'm saying? He can have it for now. You will give it back at the end of the block. You will give it back to him at the end of the block. But a lit match is going to be hotter than the iceberg. So the match has more heat, but the iceberg has more thermal energy.
That makes sense. Put your hand on like frozen ice. What's that ice called? There's like a really cold ice, and you put that on your hand, and it burns you still.
It's a different kind of burn.
Dry there?
Like liquid nitrogen or dry ice. It's a different kind of burn. It's freezer, it's not a heat burn, it's a freezer burn. The damage is different. It's equally painful, but different, yes. You bet. Okay, Angel said the next one. Sound. Sound energy is the energy of vibrations of particles. Specifically, air particles. I'm vibrating them with my vocal cords. They leave my mouth, they enter your ears, they vibrate the hairs. You have nerves that convert the vibrating of the hair into what your brain recognizes as my voice. And every voice does this differently. Yes, that is how the can and the string thing work. If the string is tight, then it carries the vibrations of your voice from can to can. Yes, absolutely. And then we've said it already, we'll say it again, there is electric energy. Electric energy is just the energy of electrons moving along it doesn't have to be a wire, it could just be any conductor. But I mean, in a perfect world, there's supposed to be wires. And then there's a whole bunch of types of potential energy. We've talked about these, or some have already too. This one is elastic. There's elastic potential energy. It's the energy stored in stretched or compressed objects. Because you can go the other way. You can compress a spring and make that really scary. Because as soon as you let it go, it wants to bounce out of your hands. This is the whole premise behind like a shock on a car. Shock absorbers. They are compressed a little bit so that your car has a little bit of bounce. It's not compressed all the way. And it's not relaxed all the way. Because your car needs to have a degree of bounce up and down as you drive to make your ride smooth. Sorry? The next one is chemical. I thought I just lost 2 people. Have I lost 2 people or just 1? Then you can go. So chemical energy is energy stored within chemical bonds. In food does this. Batteries function like this. Sugar is a molecule that is responsible for providing us with a lot of our energy. There's gravitational. It's the stored energy due to an object being up in the sky. If it can hurt you when it falls, it has gravitational potential energy. This whole column is potential. All of these are potentials. Relative to, and that's good. Okay, so for those who didn't hear Vikram's question, Vikram said, doesn't everything have gravitational potential energy? Relative to different positions in space, yeah, they do. So let's talk about this. Who else? So let's get someone new. Good, Morris. You like to be involved in things. I would like you to sit on the floor. Yeah. Have a seat on the ground. Oh, you're gonna move your chair. Don't ask you for your question. Oh, you're gonna go under the desk. Okay, so same question as before. Is this concerning for him? Should it be concerning for him? A little bit. I mean, I'm hoping he trusts me enough not to drop this on his head, but I mean, it could slip. That could hurt. Okay, nothing here has changed. It's the same height it was before. It's still above Imparis' head, but why is this now a less concerning place? Because there's something in between. So, thank you, Imparis. The difference here is, what is the place that we are measuring from? When it was just Imparis sitting on the ground, it was this thing to his face. When he slid under the desk, now when he wasn't the face anymore, it was this to the tabletop, even though the position of this thing hadn't changed. So you can choose where you measure. Which one do you want to try for? Okay. Where you measure the gravitational potential energy from and to matters and can change. Like right now, I mean, this is not a great example. Let's find something. Well, let's talk about all of us. All of us as a collective have a gravitational potential energy. Is anyone scared of our combined gravitational potential energy right now? No. What if we had an earthquake? If we had an earthquake, now all of a sudden someone might be scared. Who could be scared of our collective gravitational potential energy? Anybody beneath us. All of a sudden, a class full of students is concerning if it's possible for that class full of students to fall straight down. So yes, everything has gravitational potential energy, but sometimes we're concerned about it and sometimes we're not. It depends what you're measuring to. In an earthquake, it's totally reasonable that we wouldn't measure to the floor, we would measure all the way to the ground. Because in a really bad earthquake, if this building's not built well, we will fall to the ground. We don't need to be super concerned because there's really nothing above us. But everyone beneath us, if this building collapses, is screwed. Because there's layers of concrete and steel under our feet. And if you're on the first floor, there's 2 layers of concrete and steel between you. Yes, Angela. Yes, be fast.
I thought this building was pretty earthquake.
It is. But there's no such thing as a totally earthquake-proof building.
What if it was like a small one?
And then obviously, but again, you don't go to a class on the 2nd floor worried that the school's going to collapse. But as soon as there's an earthquake and you're on the 2nd floor, you can't tell me your brain doesn't immediately go to what if.
I think it would rather be on the 3rd floor, like get out of the building.
Or if you're going to die, you're really going to die. You're not going to get mangled. You'll be squished.
No.
Those are kind of the options, right? Either you manage to escape or you're definitely squished. There's no in between. So let's keep going. We're almost done. Gravitational. Good question, Vikram. Next one's nuclear. We're going to talk about nuclear potential energy. It's the energy that is stored in the nucleus of an atom. What does that even mean? We'll talk about it. Question number 4, the 5th one is, sorry? Yes, Malik?
For nuclear, would that also like be your phone?
No. There is nothing nuclear about your phone.
Radiation.
All of this is radiation, 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 radiation. What kind of radiation are you referring to? No, your phone operates on the same wavelength as microwaves. They would not be legally allowed to sell you these devices if there was any danger to them. There's Wi-Fi coursing through us all the time right now. Anywhere where your phone gets a reception, there is radiation reaching the phone. And if you're able to send a call, that means your phone is sending radiation. So no, the radiation produced by your phone is not a concern. They would not legally be allowed to sell them if they were. This one is electro potential. It's energy stored by the separation of positive and negative charges. And the last one is magnetic. Magnetism is all about the potential stored in a magnetic field. Let's see what time it is. What time's the bell going to go?
15.
So 2 minutes. We are going to stop right here, and we will pick it up tomorrow. By tomorrow, I mean Monday. Have yourself a super duper day, and I will see you later. Enjoy your weekend. Get out and enjoy the sun. When the bell goes, you may also go.